All right, welcome back. Cohort 5. We're in our second discussion on chapter 7. So, is there anything anybody wants to begin with? We can look at the text. We can look at any question. We can add a new question. We could look at PyMDP. Anything. Anyone can write in the chat or raise their hand or just go for it.
Yeah, so I have a sort of more open-ended question. I've been sort of thinking about, doing a little modeling project, and what I would like to what I'm thinking about is that I'm just wondering how I can use this active inference machinery to model some kind of like a recognition task. Like, how would you approach doing something like an MNIST classification with active inference? But what I am interested in is bringing this, one key difference from the active inference approach to the problem of that's basically completely solved in the using artificial neural networks, but in a way that when if you feed MNIST to like a transformer based classifier, you patchify it, so it turns into small little chunks of image, and you feed that into a transformer, and the transformer kind of like sees the whole sequence and then finally learns how to classify an image. I'm just sort of wondering, thinking about like how to find some sort of connection between doing something like that, except getting the neural network or some other kind of system to choose where to look, to sort of model the behavior to be almost like a saccade. Like I'm seeing a part of an image, and then I have to make a decision where to look next to um, you know resolve as much as uncertainty as I can about what am I seeing. And it doesn't have to be something like an MNIST. It could be like some really simple images to start with, like 8x8 pixels, some generated, I don't know, noughts and crosses or whatever. But I don't really even know where to start with that. It's a very open-ended big thing. But if you have any suggestions where to look at, I would love some pointers.
Yeah, great questions. Well, certainly what I'll show now is not the end of the story, but I think it'll provide some motifs that you can pick up on. Here's a 2021 paper with Axel Constant. So in this setting, it was an eye saccade visual. And one of their novelties was that they made a bounding box that was kind of like the zone that was visible in the saccade. So the cross focus is the center of vision, and then the affordance of the eye saccade is to move to another cross, and then that would move the bounding box. And it's a cultural pattern recognition task, like based upon identifying these higher order patterns of pottery.
Mm.
So that's one visual way. I think this is a super fascinating thing because in almost all visual recognition tasks, either the whole image is passed through if it's sufficiently small, like MNIST, or it's tokenized or chunked or however. But here we bring the action into vision with actual guided cognitive vision moving to uncertainty. So that might be way more efficient in certain settings. For example, recognizing a person, like first there's like the movement, just empirically, like there's like a movement to the body, and then there's a movement to the face, and then identifiable parts of the face. So that's the saccade model. And then on the MNIST, the recent structure learning paper actually specifically they do MNIST,
Oh, wow.
and they so the labeled data in MNIST are the true identity of the digit. And then they use their structure learning technique to develop the styles, handwriting styles of the digit. So they're not doing structure learning on how many digits there are, as far as my reading, but they do look at different styles. Like these are different styles of the digits. So then it is learning it's saying how many styles of one are there, and then it's finding through structure learning, which is the proposal of a additional latent factor, and then Bayesian model reduction, pruning the model back down for redundancy. They find strong performance on the MNIST. The code is in MATLAB, and I've looked into it. With some language models, you might be able to bring it into something out of MATLAB or just isolate it into pseudocode. But the MATLAB code itself, it's a little bit of a it integrates a lot with the broader SPM package. So it's not just like you can just pop out the MATLAB script and run it, because if you follow the rabbit's trail, it goes into a few other SPM scripts that I don't think have been brought over into PyMDP yet. But from a pseudocode perspective, it's very informative.
Awesome. That looks super relevant. Thank you.
Thank you. Yeah, but this one does not have Saccade. This one, the MNIST digit is coming in fully. One interesting thing also on the cultural one, this generative model was actually, this is before PyMDP. This generative model is the one that we utilized for Active Inference. We just said, well, what if instead of it was an iSaccade in a bounding box without leaving a trace, what if it was a nestmate moving in a zone, leaving a trace? So that kind of opened up the like observing from afar, moving your eyes, but not leaving a trace, versus skin in the game, where the movement from here to here is interpreted as a physical movement.
Cool. Great stuff. Thank you.
This paper also, I mean, has other benchmarks like the recognition sprites data set, maybe even a third one. Towers of Hanoi, classic TI-83 game. With some very interesting shapes. Cool. Any other thought or part on 7? PyMDP right now is only in discrete time. So pretty much everything that you encounter in PyMDP today will be in the Chapter 7 spirit. Sanjeev's Python work, as well as ActInf and Julia, have continuous time models. Okay, can we go through the matrices other than A to D? So you're talking about in here, Prakash, or in which figure do you?
Maybe, yeah, this seems good. Sure.
Okay. 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 So here's the progression of how they introduce the matrices in 7. O is the observation vector at each time point. So if you just had one binary sensor, O would be a 0 or 1. If you had 8 float sensors, it would be 8 float numbers. S is a vector carried through time, each time point, of the latent states. So let's say we're talking about temperature in the room, thermometer, observations, latent temperature, hidden state, S. Agent's estimate of hidden state, S. A is a matrix that has rows and columns corresponding to O and S. A is a mapping between O and S. And so it can be used to start with S and then emit a distribution of expected observations, or it could be taking in an observation, conditioning upon an observation, like Bayes' theorem does, and then updating a hidden state belief. D has the same dimensionality as S being carried through time. So D is just like a vector. It's kind of like T0. It just starts the chain going and it gives you S at the first time point. And then B is a transition matrix that has edges and rows and columns, edges of the dimensionality of S, because it maps S at T-1 to S at T. So this is a standard hidden Markov model. Ambiguity matrix A between hidden states and observations, transition matrix B between states at times. There's no action in this model yet. The next thing that they do is they take that exact downstairs model, E coming down, and then this is where the action enters the picture, which is pi, which is the policy space expressed as a probability distribution over actions. So pi sums up to 1. It could be sampled from, or it could be just pick the highest number, or it could be, pick the second highest, or all these different things that you can do regarding how to pick a policy from pi. But pi intervenes with a policy in B. And so while previously B was just a single matrix going from S of T-1 to S of T, now B is going to be having a matrix slice for every single affordance that we have. So each slice of B is like an index card that describes the world transition model conditioned upon action selection. G is expected free energy, and G is a distribution that essentially updates the policy prior habit with respect to epistemic and pragmatic value equation 2.6. So that gets us to this kind of figure 4.3 or figure 7.3 discrete time classic model. We have a downstairs hidden Markov model with no action, and then actions select which B matrix is going to be applied as S unrolls through time. And then in figure 7.10, we see a lowercase letter above each of these other letters that we've talked about. That represents a hyperprior, or however you want to think about it, but it's a distribution which that uppercase variable is drawn from. So instead of just saying, well, there's 4 states in the world, so our D vector could be 0.25, 0.25, 0.25, 0.25. That'd be like a uniform prior across initial location. Or it could be 1, 0, 0, 0, just unambiguously starting in the first distribution. Or you could parameterize little d, which would be a distribution which D, big D, is sampled from, for example, across individuals or across estimates or across trials. So then learning could happen on little d across trials. So you could begin with like a uniform prior of where I begin. And then with learning by counting, you could just say, okay, I'm going to, with the conjugate prior, the Dirichlet distribution, I'm going to add 1 count to little d every time I observe myself starting in a certain location. And then trial after trial, you'll end up drawing big D from a prior distribution that does resemble the experienced history. That's the learning by counting part. And then at the end of the chapter, they just kind of present one more motif, which is now that exact 7.3 or figure 4.3 exact motif. They're just demonstrating a little bit of the composability of the Bayes graph by showing that like the observation being emitted from a top level model here, level 2, that observation could be understood as, for example, a prior on a lower level model. But figure 4.3 or figure 7.3 is kind of where in the discrete time we get the downstairs sense making part, sense making from observations, transition world model, and then finally to the action dependent world transition model.
Yeah, thank you. I think it's a very good overview, and I'll refer it back again, but I think it's. I just have one question. When you use the word motive all the time, what does exactly mean? Like, I think I just don't understand that word actually. Sorry.
Motif, I use
Yeah,
it.
what do you mean by motive? Sorry.
I use it to like a pattern language, or like an
Oh,
identifiable theme. So,
okay.
like let's just say we were looking at cars as generative models. Like one of them is red, another one has convertible top, another one has 6 wheels, another one has a trailer. Like those are just kind of like motifs. Some motifs might be mutually incompatible, but other motifs, it might just be like, well, like, um, here we're looking at the motif of having a hyperprior. Here we're looking at the motif of nesting. Now, the lowercase letters are not shown, but of course you could have lowercase letters. So there's nothing contradictory about those two motifs. It just, and this is definitely not like the only or a formal way to think about it. It just like here in figure 7.3, we kind of have like the kernel nucleus. There isn't much you could remove here. If you wanted to remove something, you could remove like this part. So it was just focus on the transition of 2 time steps. But that's very minor. This kind of shows the basic initialization and then the step from the previous moment and then the step to the next moment of action as reweighted by expected free energy. So here we have kind of an essential kernel, and then there's all these motifs, or there's other ways probably to say it, but there's all these other strategies that we could start to see or use.
All right. Thank you.
And yeah, I mean, I don't know how far the Linux kernel metaphor will go, but like this model doesn't have, just as written, various of the more sophisticated cognitive phenomena. So it's not that advanced cognitive phenomena or higher order human type thinking is already in this image. It's like this is the canvas that is a starting point for like learning and novelty. So it's not that all these different diverse cognitive phenomena are like intrinsically, essentially within the active inference formalism per se. It's that we have something that's general and modular enough to accept and even entertain multiple different renditions of a given phenomena. Like there's not just learning. A narrow definition of learning would be like each parameter being updated. And then if somebody wanted to engage with a higher order, like kind of conversationally, what we might talk of as learning, like chapter 6 is there for us. We could go through it and we would find like a room of 10 people could come up with 1,000 ways to implement learning at a higher level in active inference. Hence, a lot of emphasis on like, what's the core? And then what are some of those like decorators and modifications, augmentations, and so on? Because chapter 6 plus the core essence plus the confidence to play with motifs gets very far.
Would people be up for maybe a little, if we take a look at figure 7.10? Would people maybe be up for trying to walk through it, perhaps like, and I don't know if this is applicable, it's a long way from the T maze, but like walking through it like with like a real life kind of decision idea. Like what I'm thinking is, and try to map that process onto the model. So like what I was thinking is like I'm sitting in my room and I'm looking outside of my window and I'm trying to decide whether I'm going to go outside or not. And like looking at, okay, what are the parameters of that decision? What are the different observable states or partial like or hidden states that are going to influence, that policy. You think that's an appropriate exercise, Daniel, or something along those lines? Would people be into that?
I mean, it definitely is. I'm just finding a table that I'll copy in. Okay. I'll make this under chapter 7. Okay. This is just one little template. So here we have the A, B, C, D, E, and pi, and O and S. So we don't have the lowercase letters yet, but we could add them. And each of those discrete time variables is linked up to an ontology term, all of which have been used. And then here is an example, like for an ant colony nestmate, how those got mapped. But I mean, let's hide these and then let's just go for it. Okay. What's the setting? What is the agent's vote?
Living room in New Mexico.
Okay.
If that makes sense, yeah.
Aren't we all? Okay, observing.
The window.
Okay, what
Outside
about
through the window. So I guess outdoors through the lens of the window.
Okay, pixels coming from outside.
Sure.
And then what's truly out there? Could be, is it raining or not? It could
Yeah,
be
the weather, I
temperature.
guess.
Okay.
Is it that's the decision I'm trying to make, yeah.
Okay. Well, and this just goes to show, like, first off, how open-ended, like, what actions are, but I mean, we'll get there, but can we control the rain? So then there's already such differences between a model where, like, there's a hidden state that you can't control, but you still could make a policy decision to, like, take an umbrella or not.
Right.
But then there would be like another level of kind of interactivity of a model when the policy can also control the hidden state, like when they're like an air conditioner with a temperature versus just sort of like a put on a jacket if it's raining. Okay, so now given that we already said S and O, what is the dimensionality of A and what is the semantics of A? Let's just say, just to be clear, that the visual stimuli that we're getting is 10 pixels, and then they have a continuous level of brightness. Like we could go into the RGB and all this other stuff, but there's 10 pixels. And then raining or not is a binary state. So what is the dimensionality of A, or what does A map?
I mean, aren't the site of raindrops or not, right? So it's like
Yes, it maps, but
So that's a 2-dimensional. Yeah.
Maps between the observations and the hidden state. So its shape is 2 by 10 matrix.
Okay, I see. Yeah.
There's other, we're just going with just the first sketch pass. Okay. So this is mapping these pixels from the pixels down to beliefs about the rain or vice versa. So if we said condition upon I know it's raining, we could emit a profile of pixels that's the likeliest thing, or we could take in an empirical pixel distribution and then ask what is our conditional probability of it being raining. So this is, and then last piece of the downstairs sense making part, what is the B matrix shape? Given it's a transition matrix.
Should be 2 by 2, I guess.
Yes. These are just the transition probabilities of staying raining, staying not raining, or switching. The identity matrix, the diagonal on B is like stay, because you're mapping from, let's just say that the first row is raining, the second one is not raining. The upper left corner on B is rain to rain, and then the lower right corner on B is not rain to not rain, and then the off diagonals are switching. Okay, this is the downstairs part. This is a partially observable Markov decision, or sorry, this is just a partially observable Markov model. No decision has come yet.
Right.
Now we're going to come into the decision. Okay, so what is the action space?
Go outside or not?
Okay, now if we go outside, then we're going to get different observations, but we'll just say yes, go outside or not. Okay. What are the affordances?
Basically, not raining. It's an affordance for us to go outside. Yeah.
Almost here, the affordances are the same as the policy space because there's no planning.
Okay.
So affordances are what you can do in a moment, like up, down, left, right. And then the policy space is the affordance space exponentiated to the time horizon of planning. So if it's a non-planning model, then affordances equals the policy space. But if it was a two-step model, then you could plan, I'm gonna not go outside and then I'm gonna go outside. Or I'm gonna go outside and then I'm gonna come back. So then that is considering over multiple time steps. But here, single time step, no plan. Okay. We need D as part of our downstairs. D is prior on it raining. And so this has the same shape as S. So this basically is just, this could be like 1, 0, which is like, we start, sure, it is raining. Or it could be 0.5, 0.5. We start unsure if it's raining. Okay. And then actions are selected different ways. Obviously, that's what we're interested in. So what are some different ways you could select actions? Well, you could just draw from your habit distribution. That's one approach. Okay, now we're going into the New Mexico dopamine brain. On the left side, this is where we have actions being drawn from the habit distribution. So that's a totally viable decision-making strategy. That's kind of like thinking fast, like type 1 is drawing from habit. Another approach is to use expected free energy to reweight the policy prior into a policy posterior. according to equation 2.6, which is to say reweighting policies according to their epistemic plus pragmatic value. So in this setting, the epistemic value, right now, like everything's pretty much fixed. So there really isn't much epistemic value to gain yet. Pragmatic value, though, is going to be about preference satisfaction. So what would the preference be? Preference is over observations. I'll just note, like, this recent one on intentional behavior, they do explore, like, essentially preferences over whether it's raining or not. But suffice to say, in the textbook and in this kind of primary version, the preferences are over observations. So let's just say that it's darker when raining, lighter when not. So if our conversational preference is like, I prefer it to rain, our C preference variable, because it's over observations, would say I expect and prefer it to be darker, because the preferences are grounded in sensory observations that haven't come in yet. I mean, uploading the textbook to a language model or not, copying in this table, and then saying, write active inference Python code, given that this is my POMDP, you will get a script with just this much information.
Wow.
Because you've given all of the information needed. There's way more complex models to make, but in terms of describing all of this, I mean, G is not really a variable. It's a functional that gets applied to pi conditioned upon C and E. So by defining A, B, C, D, E, S, O, and then the generative process, the true rain. But that doesn't have to be active inference. That could be a random number. That could be an API to a weather station. That it could just be anything else that plugs in and outputs observations and then intakes actions. But here it's kind of a null action intake, because your choice to go outside does not affect whether it's raining.
Yeah, that makes sense. All right. Yeah, thank you for that.
Cool. Yeah, I mean, plug it in and see where it goes, or look at a PyMDP documentation and see which one it looks most like. I think we looked at it a previous time, but this one is a moving grid world agent in one, and then two. Prakash, this is under chapter 7. Yeah. And then chapter 2 here is again similar. And then the I mean, make some kind of fusion variance. Like there's a T-maze. It's like your living room is the starting position in the maze. And then like, you know, you could check the weather, that's the epistemic cue, or you could choose to bring an umbrella or not. And then it would already have almost isomorphic relationship with it, with a tutorial. And especially when starting, this is like why the iterating on having a model is so informative. Like ironically or appropriately, depending on how you see it, it's epistemic chaining. The modeler is in an epistemic chain with their own modeling. It's super easy to wait on the sideline until what? I really don't know. But by putting something down, then there's all these other things that open up. So that's the epistemic chaining as a process. Okay, Francis, let me just see what you wrote. Is it straightforward to download either the PyMDP notebook? Is the chapter 7 document also okay? About PyMDP, yes, at the top of each page, like I'll just put it in the chat. You can open it in Colab, super easy, and then just make a copy. So those are very nice notebooks to pull. Is the chapter 7 document also a Jupyter notebook? No. That would probably require going to Appendix C and going to the MATLAB code, or the T-maze foraging, and bringing this MATLAB code into something like a notebook. I'm not actually sure if MATLAB even has notebook, or realistically, since it's the T-maze, like this PyMDP T-maze demo, it's the same exact thing. So this notebook is probably a good one to go with.
I don't have Colab. As a non-academic, it's expensive. Or used to be expensive. Is
MATLAB?
it? Sorry.
You said you don't have Coda or MATLAB?
Colab.
It's free. You just click on the link and then just duplicate it.
Okay.
Yep.
Right. Okay.
MATLAB does have a costly license, except there's the Octave like variant that's open source, but like rather than get into this whole like Octave MATLAB situation, like the Python and Julia are the way to go. And Rust when the time is right. This is interesting. Recommend breaking the demo to change the generative model. Only by doing this will an intuitive sense mechanics of active inference develop. Pretty interesting.
That's exactly what I was planning to do. Thank you.
Okay, yeah, I mean it's super fun. And then also like again, seeing the kernel execute, like just seeing a decision be made, that helps open up like, oh, there's like all these levels of diagnostics or analytics about the trace of the model that you might be interested in. Now, is that active inference? Well, it's about an active inference model, but then a next step might be like to do a parameter sweep across parameter combinations and then summarize the outcomes of those swept parameters with another heat map. And then what do you do from there? You know, then you could fold that back into the base model, or maybe you make another active inference agent that looks at the heat map and then does something from there. Hence it being more like lines or journeys of inquiry rather than like developing an artifact that just kind of slams the door. Especially with these kind of more intuition pump examples.
Without wishing to derail things, I have an interest in doing test automation for code, and I was looking in chapter 7 at the way that the agent explores the little maze quite efficiently because it's seeking novelty. And I was wondering whether I could do something like that to do exploratory testing of, say, an API.
That sounds very interesting. I've never specifically seen it, but something like adaptive fuzzing or testing. And then that's where the epistemic value comes into play. It's like, let's just say pragmatic value is I prefer the program to work. So, and then epistemic value is I'm going to find out about where and how it does or doesn't work. So if you only made the breaking changes that you knew were going to break it, it would be very confirmatory, but it wouldn't be epistemic because you would only have been confirming, which might be a valid exercise, but you'd only be confirming the consequences of the actions that you already suspected. But maybe that's important. And then another setting would be like with a kind of uniform prior or with an informed prior, what kinds of changes would actually reveal more learning about the structure of the program or the API. And then it's like, but once we figured out that that's a breaking change, like we've kind of mapped that part of the maze, there's probably a lot of cool ways to go there. Christoph?
So I think it's an interesting problem what to do with something like, you know, exploring an API. There's this paper, Friston, there's planning and no, sorry, not planning and navigation. Active inference in intentional behavior, and they have this notion of sort of like inductive planning, where there is a certain goal that the agent wants to reach, and it works backwards to figure out what are the steps to get there. For something like, you know, exploring an API, and I think for a lot of applications, though, I think what's going to be eventually necessary somehow is to have a hybrid model that you will have to be able to attach almost like an LLM to it to basically at some point say like, well, I would like to actually, you know, I decided on my course of action, I want to write some code that actually invokes the API. And here with this decision, the structure of decision making, we're looking kind of like at assembly level of intelligence, and at some point, just like we are attached to an LLM that continuously pumps out words, and I'm just, you know, sort of choosing over the distribution of those words as they're being pumped out, but I'm not actually generating them, right? Like I'm not aware of how that's happening. In the same way, you would have to kind of attach an LLM to almost like an active inference agent that does some kind of goal-oriented exploration of the API. So that would be very interesting if you could achieve something like that. And it's probably, you know, quite a lot of money to be made on this sort of intelligent exploration of APIs, given how much trouble bugs are causing.
Cool.
Thanks.
Yeah. Like, and then in kind of like in that like we were talking about right before we began with like the feedback and the training examples, like you could have a data set of correct API calls and incorrect API calls or something like that. And then it's like plan to make it work. And those are kind of the semantics of perception and action that, like ecosystems of shared intelligence, synthetic intelligence, if we can construct a formalism that has the semantics that are how we think about it, and or co-evolve that with updating how we think about it, then we would have kind of a high bandwidth or a low loss or some other good property of the edge between us and the constructed artifacts.
Yeah, I think this is where, you know, like LLMs really kind of suck at that. You can sort of ask it to do something like this, but it will not really have any kind of notion of thinking about the problem deeply, about how would you go about breaking something for an API, because that requires a sophisticated model of what the API might be doing under the hood, for instance, like some kind of buffer overflow and something like that. But if you could come up with a minimal example that would model something like, assume there is a possibility of a buffer overflow in an API, how would you go about making some kind of inference about or planning to exploit that? That'd be super interesting, like, as a minimum, as a kind of a minimum example, even for just a simple, very simple API that takes like a car star and a size or something like this. How would you go about, inferring whether it's possible to do the buffer overflow in this?
One funny piece there would be check out the PyMDP API, and then what would be appropriate with the appropriate the latitude within that API is active inference. That's kind of one that would be a plot twist. And then also on the interpretability, here's a paper with Mao and others from last year. Like largely there aren't technical advances in this paper. The images are drawn from Sanved Smith's Livestream 28 paper. So it's not like this is breaking new theoretical ground, but the whole point is when you ask a neural network or LLM, etc., how sure are you about that? It can come up with a sequence of tokens, but that sequence of tokens is only going to be coincidentally related to anything like an uncertainty evaluation. Whereas if uncertainty parameters are explicitly encoded, then self-access introspection is just like a parameter lookup. It's not like some second, it's like part of the real-time function of the system is uncertainty estimates of different kinds at different levels. So then to ask about how certain it is about a certain thing at a certain level, you just ask that question and then return that variable. Maybe even that's on some kind of special chip or something like with verified access or something. So it opens up to all these different architectures rather than like, well, let's train like another adversarial neural network to like, try to infer this about this one. And then that gets into this whole like deception game versus having these introspectable architectures. Joris?
To what extent does this differ from Bayesian reinforcement learning?
Great
Or is this?
question. What about that, or what do you mean overall? How's active inference different than reinforcement learning? Or
yeah, maybe indeed even overall, but yeah, if you want this kind of uncertainty measure with whatever you infer, then I guess both frameworks will allow this, or is there? Yeah, it's probably a very
Yes.
unclear question, but
Yeah, okay. There's a few works and a few approaches there. So models that aren't active inference still do deal in uncertainty. So there still is an uncertainty parameterization in even a linear regression. However, a neural network or reinforcement learner that's trained to generate language, its outputs of languages don't necessarily represent a veridical introspection. Maybe there's a way to train it so that the output is a veridical representation, but that would be a secondary kind of welding together. Whereas this architecture that we just looked at, like it's intrinsically part of it. So that's kind of on the uncertainty as part of the architecture part. The key difference between active inference and the reinforcement learning is in reinforcement learning, a reward distribution is proposed. Secondary or auxiliary or corollary distribution is proposed that's like layered over the observations. So in the homeostatic environment, we'd say we're getting observations about temperature and we are rewarded by 37C and we seek out high reward. In active inference, we do away with this secondary auxiliary function and we directly work on the observation distribution by calling our preferences, not a preference for higher score on this proposed distribution, but rather we have an expectation and a preference that connects directly to the observations themselves.
Yes, I understand that, but I have been vaguely looking at things that Benjamin van Rooij and his lab are doing, but I don't really understand it yet. But there is some kind of thing like Bayesian reinforcement learning, and I wonder if they have. I would expect it to have a measure of uncertainty that comes with any prediction there, but I might have it might just be a too vague concept in my mind.
No, you're right. There it is there. I mean, this work on demystified and compared, and there's several other works that do directly tackle it. It's not out of the picture that, I mean, architectures can include arbitrary components. So it is possible to be like, well, let's have an epistemic module. Well, yes, but then epistemic and pragmatic value at the end of the day in the RL learner or the deep Q learner or whatever, epistemic and pragmatic value are going to get blended back together into the reward function.
Right. You have these like artificial curiosity and other intrinsic motivations that you could add on to a classic canonical reinforcement learner. And I see quite a lot of research on that. But then it seems that from an active inference framework, it kind of emerges from the system. But
absolutely, that is the hope. Like that there's a variety of cognitive phenomena, from planning to epistemic value, curiosity, intentionality, variety of phenomena that could be implemented in a range of architectures, but will pursuing a first principles approach lead to simpler, more interpretable, more efficacious models? Possibly. If somebody needed, there might be a better model for a situation today, because there are such incredible gyms and toolkits for reinforcement learning. But yes, hence the moment of the epistemic excitement that we have and share here, plus the accelerating pragmatic conversion and understanding, like, yeah, where is this useful? Because it's all good for something to be insightful, but then I mean, there could be a situation where active inference just gives us an intuition pump and then we use a neural network, or there are hybrid architectures that do this or that. And but if utility is what is desired, or some other property that another system already has, then yeah, definitely active inference has to work to be superior there. One really interesting moment from this was a couple days ago with Ryan Smith and two of his PhD students. So the empirical status of predictive coding. What was super interesting about this paper was, like, in this textbook group, if someone said, like, what's the status, like, of FEP or status of ActInf, people would often take it like in a metaphysical direction. However, they took it the other way and asked, what's the empirical status of predictive coding and active inference in explaining neuroimaging and neurobiology? So it's very interesting, and these are the ongoing questions. And curating the models and being able to compare them based upon how they do treat these phenomena, that would be super informative. And then if we can have a similar syntax for the variable, similar API, use agent. I mean, the demystified and compared, it uses the OpenAI gem. So like they presented some promising, interesting results, and that was several years ago. And a lot of the work has probably not been published on the OpenAI Active Inference side, but it is right there, like with Frozen Lake or with the other reinforcement learning settings. And then look at where they're different, find out where does the super high performance, large scale RL model do well that this simple ActInf one doesn't. And then what would we need to do to make it different? Well, fun. Yeah, chapter 7 is pretty fun. Next week's we'll head into chapter 8 on the continuous time. Maybe we'll look at some RX and FIR examples because there aren't going to be PyMDP examples for chapter 8. The continuous time models, there's a lot to say there on the math and on the philosophy and so on. Chapter 9, integrating with data. And then chapter 10, just a long wrap up with no figures or equations. So thank you all. See you next time.
Thank you, Daniel.
Bye.
Thank you.
Thank you,
Thank you very
Daniel.
much.
Thanks, everybody.
Cool.